All right, let's dive in today into something that's always there, but we never really think about it.
Hmm.
Earth's gravitational field.
Oh, that's a good one.
We've got some cool excerpts here from Open Educational Resources slash,
Open source physics at Singapore.
that's the one.
Hmm.
Let's see what we can uncover about this kind of invisible force, shall we?
Yeah. It's amazing, isn't it? Like, we go about our day, walking, jumping, even just sitting here,
Yeah.
totally ignoring the fact that we're constantly being pulled towards the center of the earth.
Yeah, just sort of there, like an invisible tether, you know? And the source material, it even starts with this really basic question. How can objects exert forces on each other without even touching?
Yeah.
So what is this magic?
Right. Well, that's where this whole concept of a gravitational field comes in.
Okay.
Not magic, but it's pretty mind-blowing when you really think about it. Every object with mass creates this field around itself.
Huh.
A region of influence, you could say, like an invisible aura, extending out into space.
Okay, so Earth has this giant aura, and everything on its surface is feeling the effects.
Exactly.
But what about things further out?
Yeah.
Like way out in space? Does Earth's gravity affect them too?
Absolutely. It does. The strength of the field, that pull, it diminishes with distance. So the further you get from Earth, the weaker its gravitational influence becomes.
The source material, they mentioned field lines
Yeah.
as a way to visualize this, and they even have this interactive simulation. You can check it out yourself at http://iwant2study.org/spsgendex.php55.
Yeah, it's a good one.
What's so cool about these field lines?
Well, think of them as a map, right? A map of the gravitational force.
Mm.
And the closer the lines are to each other, the stronger the force is in that region. So near Earth's surface, where gravity's pull is strongest, those lines are bunched up close together.
Okay, so I'm picturing these lines all crammed in around Earth. What happens to them as we move further out into outer space?
Well, as you venture further away, those lines become more spread out, visually representing that weakening gravitational influence. If you were to zoom out to a cosmic scale and look at Earth's field lines from very far away, they'd be barely visible, indicating just how much weaker the force is at those distances.
That simulation, it has different settings for outer space and very outer space, right?
Yeah, it does.
Does that show how dramatically the field lines change as you move further away from Earth?
It does. It's a great way to see how the strength of the field drops off significantly the further you travel from the source of the gravity.
Okay, that's starting to make more sense. But here's the thing.
Uh-huh.
I get that these fields exist, but why should I care? Does understanding this really affect my day-to-day life?
Well, you might be surprised. For one, understanding these fields is crucial for space exploration. Imagine launching a satellite. You need to factor in Earth's gravitational pull at different altitudes
Okay.
to ensure that satellite stays in orbit.
Oh, I see. Yeah. You don't want to launch a multi-million-dollar piece of equipment only to have it come crashing back down to Earth.
Exactly.
Because you miscalculated the gravity.
Yeah.
So it's like finding that right balance between the satellite's speed and the pull of gravity.
Precisely. And it goes beyond satellites.
Okay.
Planning missions to other planets requires an even deeper understanding of how gravitational fields interact, both Earth's
Yeah.
and those of the planets you're trying to reach.
So it's not just about launching things into space. It's about navigating the gravitational forces of other planets as well. Are you telling me that every planet has a different gravitational field strength?
Yes, each celestial body, from planets to stars to even black holes,
Yeah.
has a unique gravitational field depending on its mass and density. This means that navigating space is a complex dance with gravity, constantly adjusting trajectories and speeds to account for the varying forces at play.
That raises a pretty fascinating question then. How do the gravitational fields around those other celestial objects like black holes or giant stars,
Yeah.
how do they compare to Earth's? I mean, black holes are known for their incredibly intense gravity, right?
That's a great point, and something that deserves a deeper dive. Black holes are indeed fascinating when it comes to gravity.
Okay.
Their gravitational pull is so strong that not even light can escape, which makes them some of the most intriguing objects in the universe.
And what about giant stars? I mean, they're massive,
Yeah.
but also much bigger than planets.
Right.
Does their size affect the strength of their gravitational fields?
Absolutely. It's not just about the mass, but how that mass is distributed.
Hmm.
Giant stars, despite their huge mass, have relatively weaker gravitational forces at their surfaces
Okay.
because their mass is spread out over a larger
So
area.
it's a bit like spreading a jar of peanut butter over a giant slice of bread
Uh,
versus a tiny cracker. The total amount of peanut butter might be the same, but the thickness
right.
and intensity of the peanut butter experience is very different.
That's an excellent analogy. The concentration of mass plays a crucial role
Mm.
in determining the intensity of the gravitational field.
Yeah.
And this applies not just to stars, but to all celestial bodies, including Earth.
Okay.
Yeah.
Good.
It's interesting to think about how we visualize these gravitational fields. We've talked about field lines, but with something like a black hole, those lines would look very different from Earth's.
Now that you mention it, I'm trying to picture it with Earth. The field lines spread out as you move away, showing how the force gets weaker.
Mm.
But with a black hole, wouldn't those lines be doing something completely different?
Exactly. Instead
Mm.
of spreading out, the field lines around a black hole would be intensely concentrated, converging towards a single point at the center called the singularity.
So it's like all those lines are getting sucked into that central point, representing that immense gravitational pull that nothing can escape.
That's a great way to visualize it. And this difference in field line behavior highlights the key distinction between a black hole's gravity and Earth's.
Earlier, you mentioned that black holes even warp the fabric of space-time. That sounds pretty intense. I mean, I can picture a bowling ball on a trampoline creating a dip.
Yeah.
But how does a black hole actually warp space-time?
Well, it's a complex concept, but imagine space-time as a flexible sheet. Massive objects like planets and stars create dips in this sheet like the bowling ball on the trampoline. But a black hole's mass is so incredibly concentrated that it creates a much deeper, more extreme curvature.
Okay, so it's like taking that bowling ball and replacing it with something infinitely denser and heavier. Does that mean anything that gets too close to that steep curve just falls in and can't get back out?
You get it. That's why black holes are often depicted as these cosmic whirlpools pulling everything in their vicinity towards their center. And even light, the fastest thing in the universe, can't escape the gravitational pull once it crosses a certain boundary called the event horizon.
So even if you had a spaceship with warp drive, you couldn't escape a black hole once you cross that event horizon.
That's the current understanding. Yes, the event horizon acts like a point of no return.
That's both terrifying and fascinating. At the same time, now we've talked about black holes with their extreme gravity, but what about those giant stars we were discussing earlier? How do their gravitational fields compare to Earth's?
Giant stars are fascinating because they represent a different kind of gravitational scenario. Even though they have much greater mass than Earth, their size also plays a crucial role.
Right, we talked about that peanut butter analogy. If a giant star's mass is spread out over a larger volume, does that mean the gravity you'd experience on its surface might not be as crushing as you'd expect?
Exactly. The gravitational force at the surface of a giant star might not be that much stronger than what you feel here on Earth, despite the star having a much greater overall gravitational influence.
So it's like the force is more diluted?
Precisely. A giant star's mass is spread out over a larger area, which means the gravitational force at any given point on its surface is less concentrated compared to a more compact object like a black hole or even Earth.
Wow, so size really does matter when it comes to gravity. It's not just about how massive an object is, but also how that mass is distributed.
You've hit the nail on the head. This concept of mass distribution even applies to Earth's gravitational field.
Wait, really? I thought Earth's gravitational pull was pretty consistent everywhere on its surface.
While it's relatively uniform, there are subtle variations in Earth's gravitational field strength, depending on factors like altitude, the density of the underlying rock, and even the movement of the Earth's mantle.
You're telling me that gravity can actually vary slightly depending on where you are on Earth.
Absolutely. These variations, called gravitational anomalies, are actually quite useful for scientists.
Okay, I'm intrigued. How are these gravitational anomalies useful?
By measuring these subtle differences in gravity, scientists can actually map out what's happening beneath Earth's surface.
So you're saying gravity can be used as a tool to explore what's hidden underground.
Exactly. It's like having an X-ray vision for the Earth by analyzing gravitational anomalies. Scientists can detect things like mineral deposits, underground water reservoirs, and even variations in the Earth's crust.
Wow, so gravity isn't just this force that keeps us grounded. It's a powerful tool that can help us understand our planet in incredible detail.
Precisely. And these variations in Earth's gravitational field, while small, can have significant implications for understanding our planet's structure and geological processes.
Okay, so we've journeyed from black holes warping space-time to giant stars with surprisingly diluted gravity, and now we're back to Earth, where gravity is being used to map out hidden underground treasures. This has been quite a gravitational adventure.
It's been a fascinating exploration of this fundamental force that permeates the universe. And remember, we've only scratched the surface of understanding gravity's full complexity and its implications for everything from the formation of galaxies to the very nature of time and space.
I know it's mind-blowing to realize how something we experience every day can be so profoundly mysterious and powerful.
Exactly. And speaking of everyday experiences, let's bring this back to you, the listener. Why does understanding Earth's gravitational field matter to you here and now?
You know, we've been talking about black holes and giant stars and even using gravity to peek under Earth's surface, but
Yeah.
it's easy to forget that gravity's like right here, right now, in
Uh-huh.
our everyday lives.
Yeah.
What are some ways it affects us that we might not even realize?
Well, I mean, think about something as simple as pouring a cup of coffee.
Okay,
The reason that coffee stays in the cup
right.
and doesn't float away is because of Earth's gravitational pull.
Okay, that's pretty basic, but
Right.
surely there are more interesting examples than just keeping our coffee from defying gravity.
Absolutely. Remember those tides we talked about earlier?
Yeah.
That's a direct result of Earth's gravitational interaction with the moon.
Right, the moon's gravity is tugging on the oceans, creating those bulges of water that we experience as high tides.
Exactly. And it's not just about the oceans. Earth's gravitational field also influences the atmosphere, weather patterns, and even the shape of our planet itself.
Okay, so I'm trying to wrap my head around how gravity shapes the Earth's shape.
Uh-huh.
I mean, I know the Earth is round, but how does gravity play a role in that?
Well, it's all about balance. Gravity pulls everything towards the center of the Earth.
Okay.
And over millions of years, this force has molded the Earth into a sphere, the most stable shape for a large, rotating object under the influence of gravity.
So gravity is like this cosmic sculptor,
Yeah.
constantly shaping and molding our planet.
In a way, yes. And it's not just about the big picture stuff.
Okay.
Understanding Earth's gravity is crucial for many technologies we rely on every day.
Give us some examples. How does gravity impact our tech?
Okay, well, think about GPS navigation. Those satellites orbiting Earth, they rely on incredibly precise timing signals to determine your location.
Right.
But those signals, they're affected by the difference in gravity between the satellite's position in orbit
Okay.
and your position on the ground.
So if we didn't account for those gravitational differences, our GPS systems would be way off.
Exactly. Without taking gravity into consideration, your GPS might tell you you're in the middle of a lake when you're actually driving down the street.
Yeah, I see your point. Accurate GPS is definitely something I take for granted.
Yeah.
Any other tech that relies on understanding gravity?
Well, think about air travel.
Okay.
Pilots and air traffic controllers, they need to factor in gravity
Right.
when calculating flight paths, fuel consumption,
Uh-huh.
and landing procedures.
So gravity is basically the unseen force that keeps our planes from falling out of the sky.
You could say that. And it's not just about keeping things up in the air.
Okay.
Gravity also plays a key role in renewable energy technologies.
I'm curious, how does gravity factor into renewable energy?
Well, think about hydroelectric dams.
Okay.
They harness the energy of falling water,
Right.
which is driven by, you guessed it, gravity.
Ah, so the water's downward flow, powered by gravity,
Yes.
spins the turbines that generate electricity. That's pretty clever.
It is. And as we explore new frontiers in space travel, understanding gravity will become even more crucial.
Speaking of space travel, earlier you mentioned that even with warp drive, you couldn't escape a black hole
Right.
once you cross the event horizon.
Yeah.
So is there any way to escape a black hole's pull?
Well, that's a question that still puzzles physicists. The event horizon is considered a point of no return,
Yeah.
at least according to our current understanding of physics.
Right.
But who knows? Maybe someday we'll discover some new physics that challenges those assumptions.
So there's still a lot we don't know about gravity, even after all this discussion.
Absolutely. Gravity remains one of the most fundamental and mysterious forces in the universe.
Yeah.
We're still learning about its full implications and how it shapes the cosmos on every scale.
This deep dive has been an incredible journey.
It has.
We've explored this invisible force that shapes our world, from the mundane to the cosmic. I'm walking away with a newfound appreciation for this force we often take for granted.
It's been a pleasure exploring these concepts with you, and to our listeners, I encourage you to keep pondering the mysteries of gravity. It's a force that affects us all, whether we're sipping coffee or contemplating the vastness of space.
That's a great takeaway. So, next time you feel your feet planted firmly on the ground, take a moment to appreciate the invisible force that keeps you grounded and shapes the universe around you. Thanks for joining us on this gravitational adventure.